Okay, today we're going to start Chapter 7, and Chapter 7 is on similarity. Lesson 1 is on ratios in similar polygons. And I just want to take a second to review a couple terms, things that you would have talked about in middle school and in your Algebra 1 class as well. First of all, a ratio is a comparison of two quantities. And you can write a ratio a few different ways. One way, if I had the ratio A to B, you might see it written in words. You can also see a ratio written with a colon. And how we are going to talk about our ratios, we're going to write them as a fraction, A over B. So you can write those different ways. We always want to make sure, though, that our ratios are simplified. And because it's a ratio comparing two quantities, we always want two numbers. Now, a proportion is an equation that states two ratios are equivalent, which we know means that they are equal. So if I were referring to my ratio as a fraction, my proportion is going to show two equal fractions. When you have a proportion, your cross products are equal. And so if I had A over B and C over D, if they were a proportion, they would be equal. My cross products equal would mean that the product of AD would be equal to the product of BC. It might be a little easier to look at that as numbers. 2/3. And if I had over 60, let's say actually we're trying to find that top number. We weren't sure. You solved your proportions in middle school. A lot of times you used your cross products. If I know this is 120, that's going to be equal to 3 times x. And we would find out, well, x would have to be 40. Here, knowing 3 to 60, I also know that I would be multiplying by 20, and so I have to take 2 times 20 to find that x value. Now, in my similar polygons, they have the same shape, but not necessarily the same size. Okay, so in my diagram here, I'm showing you triangle 1 and 2 are similar. And the symbol for similar is this little squiggle, where you can see that here triangle 1 is not similar to triangle 3. I also like to think about it, if I took triangle 1 and I enlarged it, I could map it directly onto triangle 2. That would be similar, where we know if we enlarge triangle 1 over here, it would not map directly to triangle 3. Okay, so in our book, they define our similar polygons a little bit more formally. It says that two polygons are similar if and only if their corresponding angles are congruent and the corresponding side lengths are proportional. So in the diagram below, we have two quadrilaterals, and I have quadrilateral ABCD and EFGH. They are similar. I know this because here I am given a similarity statement. I'm going to make that note there. That is a similarity statement. And just as before when we wrote our congruency statements, the order of the letters is important, so they need to be in corresponding order. Now here I can see that my angles are congruent. Angle A is congruent to E, B is congruent to F, and so on. And when I check the corresponding sides, when I check A to B and E to F. Well, A to B is 6 and E to F is 12. And then I go ahead and I check B to C, 5.4 over 10.8. I can see they all have a similar ratio. And in the end, if we would check each pair of sides, we would say that that similarity ratio is 1 to 2. Now I am comparing here the small to big ratio of 1 to 2. However, if I were comparing big to small, that would be a ratio of 2 to 1. Now the similarity ratio, the definition of that, says that it is the ratio of the lengths of the corresponding sides of two similar polygons. And it's very, very similar to thinking about that as the scale factor. The only difference would be is that sometimes your scale factor, if my scale factor, or here my ratio was 2 to 1, we may just refer to that scale factor as 2, so it may not be written as a fraction. Now my similarity ratio, when we write these, we want them as fractions, but we want them reduced. We want no decimals and no mixed numbers. Okay, so let's take a look at a couple examples. In example A, they're asking us to determine whether our polygons are similar, and if so, they want us to write the similarity ratio and the similarity statement. So as I look at my figure here in number 1, they tell me I have two rectangles, ABCD and EFGH. If I have a rectangle, first of all, we know that we have 90-degree angles. I also know that my opposite sides are congruent. So I'm going to label a little bit. If I'm checking whether they're similar, they have to meet two conditions. Number 1, are the angles congruent? So I'm going to say, yes, I have all 90-degree angles. Number 2, are my sides proportional? Well, if we go ahead and check, there's a couple different ways you can look at this. But I'm going to go ahead and check my corresponding side, B to C and F to G. Well, I would be looking at 9 to 6. I can see, well, that's a ratio of 3 to 2. I need to check my width as well. Large to small, 6 to 4. That also reduces 3 to 2. So yes, I'm going to say these figures are similar. And my similarity statement in corresponding order, I'm just going to say ABCD is similar to EFGH. This is my statement. And my ratio would be a ratio of 3 to 2. Now, I could have also determined if my sides were proportion. Maybe I could have taken 9 over 6 and 6 over 4, and I could have checked the cross products. Well, this would be 36, and this would be 36, and so, yeah, I would be able to determine them to be similar. But in order to get my ratio, then I would have to take one of those fractions and reduce it. Another way is that sometimes kids divide these out and they might find the decimal. This is 1.5 and this is 1.5. And so that would tell me that those sides have the same ratio, but again, to come over here and write it, I want it in fraction form. Now, as I look at picture 2, I see that I don't have all of my information. I'm going to have to do some figuring. I have some isosceles triangles, and it looks like my sides may be in proportion, but when I take 180 degrees minus 36, and I find my missing angle measures down here, that's actually going to come out 72 degrees and 72 degrees. Well, 72 degrees and 62 degrees is not equal. And so here, my angles are not congruent, and so I'm going to say these are not similar. Picture number 3, we have another set of triangles, and I can see angle A corresponds to angle D. E to B, they are congruent, and so by the third angle theorem, angle C is going to have to be congruent to angle F. If I want to go ahead now and check if my sides are proportional, so my angles are congruent, I want to check if my sides are proportional. I'm going to take my short side here, AC, compare it to this short side. And so I'm going to compare 16 to 12. I know that 4 goes into both of those, so that gives me 4/3. Now let's compare the medium side, 20 to 15. We want to see, do we get the same thing? 5 goes into both of those. Okay, and finally our longest side, 24 to 18. 6 goes into both of those. Okay, so these are all equal. So I can say, yes, my triangles are similar. My similarity statement, if I say triangle ABC in corresponding order, then I need to say triangle DEF. And my ratio would be a ratio of 4 to 3. Now, what about a ratio of, if I turned it around, 3 to 4? Well, in my similarity statement, because I said my big triangle to my small triangle, my ratio has to follow the same, big to small. If I turned it around, that would be okay, but then my statement would need to be turned around. So triangle DEF, similar to ABC, would have a ratio of 3 to 4. We can use similar polygons to solve for some missing information. In my example B, it tells me that ACDF is similar to VWYZ. They want me to find my value for variable X and variable Y. Now, it may be helpful to mark the corresponding angles. Angle A corresponds with V. Angle C corresponds with W. And angle D corresponds with Y. Now, if I'm looking to solve here, I can see actually this figure is rotated. So, if I'm looking for, first of all, what would be my ratio that I could use? Well, the two corresponding sides that match up, I see side 9 here is going to correspond with side 6. That actually tells me my ratio of 9 to 6 would be a ratio of 3 to 2. I can use either or in my calculations, but if I were to set this up, I know that that ratio, 3 to 2, is going to have to hold true when I'm solving for x. Well, x corresponds to 10. If I did big to small, then I'm going to say x over 10, and I'm going to look at solving for my cross products. Looks like we have 30 equal to 2x, and that x is going to equal 15. And some of you could have just solved that mentally, and that's fine. Now, could have I used 9 to 6 instead? Yes, this is simply just a reduced version of that, so that would be fine as well. If I take my same ratio, 3 to 2, now I look to solve for my value for y. Well, I can see 3y minus 1 then is going to correspond to 12. I need to make sure I put 12 on the top, that's to the bigger figure, and 3y minus 1 on the bottom. If I look at my cross products, well, 2 times 12 is 24. This is going to be 3 times the quantity, 3y minus 1. And so this is going to require me to do some distributing. And then I can go ahead and solve for y. Add 3 to both sides. Divide, and we find out y is 3. Last one, number 2. Number 2 asks us to find the length of the model to the nearest 1/10 of a centimeter. So here we have our racing car and our model car. Obviously, they're going to be similar. Their dimensions are going to have the same ratio. Again, there's different ways that you could set this up. If I'm looking at corresponding sides, 1.8 meters is going to correspond to 6.3 centimeters. So I can go ahead and set that up. And maybe since I'm solving for my missing side, I'm just going to leave this as my ratio. I see my 5 meters corresponds to x. And I can set that up as so. I can do this because meters over centimeters will match over here, meters over centimeters. So I actually don't have to do any converting. I can take a look at my cross products. 6.3 times 5 is actually going to give us 31.5, and we would have 1.8x. Now we are looking to solve. We would divide, and we would find out 17.5 is equal to x, which would tell me that x is 17.5 centimeters. Now that's not the only way that you could set that question up. You actually could set that up in another ratio. You could compare width to length, 1.8 meters to 5 meters, equal to 6.3 over x, and solve that way as well. You will end up with the same answer because your cross products end up being the same. Okay, if you have further questions on this, please stop in and see me.